Welcome to Integrals Applied Electronics Part 3. All right, our first problem here, we've got a current that is I equals 1 times 10 to the negative third power times t to the half power is applied to a series RC circuit where R is equal to 88k ohms and C is equal to 1 microfarad. Find the formula for the impressed voltage as a function of time and assume that the initial capacitor voltage is at 100 volts. So we're going to start with our formula. Vg is equal to, this is the Kirchhoff formula where voltage is in a closed loop add. So these are series voltages. And we're going to do R times I, which is just Ohm's law, equals volts, plus, because the problem has a capacitor in it, we're going to do 1 over C times the integral of I dt. Now we take the integral of I dt, and when we do that, we need to put a plus C. Our plus C is the 100 volts, and so now we can just simplify our formula, and we get a Vg is equal to 88t raised to the half power plus 666 2/3 times t to the 3 seconds power plus 100. All right, our next example, a series circuit where L is equal to 0.1 henries and C is equal to 100 microfarads, has applied to it a current of I equal to 0.1 amps. From t equals 0 onward, find A, the formula for the voltage across the circuit, and B, the rate of change of the voltage at t equals 2 seconds. Assume that Vc is 0 when t equals 0. Okay, we're going to go back to our Kirchhoff formula. Vg is equal to Ri plus the inductance, or the inductor, L, times di dt plus 1 over C times the integral of the current. So we know that I is equal to 0.1 amps. How does it say? It says from t 0 onward. So there's no, t is not a factor in current, it is just 0.1 amps. So if we take di dt of I, we get 0. So our formula Vg, we have no R in this formula, or in the original question, so that's equal to 0. So R times I is 0, and our di dt is 0, so the second part of the formula is 0 also, leaving us with a Vg equal to 1 over 100 microfarads times 0.1 t. So part A in the question is asking to find the formula for the voltage across the circuit, and that would be our Vg is equal to 1000 t anytime. And part B is asking for the rate of change of voltage at 2 seconds. So to find the rate of change, we're going to take the derivative of Vg. So that gives us, because the t essentially goes away when we take the derivative of Vg, giving us dV dt is equal to 1000 volts per second. Now there's no t, specific t in that formula, so at 2 seconds, the rate is the same at 1 second or 3 seconds or any seconds because there's no t. So the answer for part B, at 2 seconds, the dV dt is 1000 volts per second. Okay, in a series RCL circuit, let R be 10 ohms, C 10,000 microfarads, and L 10 henries. Through this circuit, we pass a current I equals to 1 minus t to the half power in amps. Find the total voltage across the circuit when t equals 4 seconds. Assume that V equals 0.25 volts when t equals 1 second. Okay, so we've got our original Kirchhoff formula. Vg is equal to Ri plus L di dt plus 1 over C times the integral of I. Now we know that I is equal to 1 minus t to the half power in amps, so we can find the di dt of this one. Di dt is equal to negative 1/2 t to the negative 1/2 power. Now we can put in all of our knowns here, our resistors and our inductor and our capacitor and all of our T's. And we get a formula that's there on that second major bullet point, but we don't know what C is. We were given V is equal to 0.25 volts when T is equal to 1 second. So what we need to do is solve for C, find out what our C is, and the C remains constant throughout all times. Okay, so we've got 0.25 volts is equal to our formula that we just calculated, and we're going to put in the time of 1 second because we know at 0.25 volts that is a time of 1 second. And we solve all that, we do all that math, and we find that C is equal to minus 28.083 volts. Now that we know what C is, we can find the voltage VG at T equals 4 seconds. So we're just going to put C in, the 28.083 volts, or negative 28.03 or 83 volts for C, and now we can substitute in 4 seconds for time. Do the math there, and we see that we get a VG equal to negative 173.916 volts.